It's a great opportunity for us to have one of our key partner vendors, NVIDIA, here to talk about GPUs and various applications in deep learning, and to have all of you learn something about that technology. As many of you know, we have a growing number of NVIDIA GPUs installed on our HPC clusters here at Yale, and they're used for a variety of purposes, not just deep learning, but deep learning is certainly one of the up-and-coming growing areas of application for GPUs at Yale. And we're very pleased to have NVIDIA here for 2 days to provide some significant training to you. For those of you who don't know much about the Yale Center for Research Computing, we've been around now for somewhat over a year, and we are the people who run the large computers at Yale for science and other forms of research. And we actually have users that span the range from science and engineering on the one hand all the way to social sciences and humanities at the other end of the spectrum. And it's open, the facilities are open to all Yale students, faculty, and research staff at no cost for usage. And we welcome all of you, if you haven't already been using the HPC cluster, certainly to come and see us, and we would be very happy to introduce you to the clusters. We offer a variety of training classes on how they can be used in research, and we certainly encourage you to come and join us and take part in what we think is a great new facility to really advance science at Yale. So with that, what I'd like to do is turn it over to our two presenters from NVIDIA. This is Brad Palmer, and this is Barton Fisk. And I will leave it to them to introduce themselves and to introduce the topics that they're going to cover today and tomorrow. So let me, with that, hand it over to Barton, and I hope you all have a great seminar. I know that some of the people from the Yale Center for Research Computing will be in and out of the room to observe, and we will look forward to talking to you if you have any questions. Thanks.
Great, thanks, Andy. Can you hear me all right? Very good. Good morning, everyone, and thank you for joining us. Really appreciate the opportunity to be with you and be present to talk today about, and tomorrow, about several topics that are near and dear to our hearts, and we're hoping to share these insights and technologies with you, and sort of collectively we'll move forward into a hopefully new set of understandings about OpenACC, about GPU computing, CUDA, and our most recently announced Volta architecture. So that's today's agenda. Let me make sure I can get to the next. And then tomorrow's agenda. And this has been on the sign-up site, so hopefully you've had a chance to think about some of these topics. Most of what I want to do in this session is provide some very high-level sort of background on myself and on Brad and on our remote speaker, Matthew, who will be presenting later today. And then I'm going to give you sort of a quick summary of our GPU technology conference highlights. And then we'll dive into some more technical details with Brad. So my role really is an advocate for higher education to and from NVIDIA. That's sort of the simplest way that I describe what I do. I also go by the title of extinguished engineer or slideware engineer. I have a computer science background. I did write code. I've had quite a, I'll just say, interesting past in the industry. But these days, I really get an enormous amount of satisfaction of interacting with academia and being in this environment. And so 2 years ago, the opportunity came along for me to join NVIDIA and to take on this role. And I really, this is probably the most fun I've had in the industry in my 25 years. So I'm based in the greater Boston area, as is Brad. We drove down yesterday through the rain, so that was familiar New England experience, but not necessarily the most pleasurable one. But in a nutshell, that's me. Brad Palmer is our solution architect, also supporting higher education and research. He's almost 9 months in now, so he's an old hand. We've been hiring like crazy. Although I play the role of university relations and so on, we have a separate recruiting group, but if anybody is interested in working at NVIDIA at some point, please feel free to talk to us about that and we can get you connected to the right people. So Brad joined in November of last year, and he's our subject matter expert for high-performance computing for the NVIDIA DGX which we'll be talking a little bit about today, and for the Pascal and Volta GPU architectures. So thankfully we've got the right guy in the room. Matthew Colgrove, he's actually remote. He's in Portland. He's part of the PGI Compiler and Tools Group. I'm not sure if you're familiar with PGI, but NVIDIA actually acquired PGI about 4 years ago. They make some of the highest quality, best software development and debugging and integration tools. It was I'll use that word quite a bit. Jensen Huang is our CEO. It was Jensen's vision that they leave PGI essentially unchanged, so that group could focus on what they do best. But Matthew works in that group, and he'll be leading you through the OpenACC portion of the curriculum later today. So with that, that's kind of our high level introductions, and then I'd like to go and just talk to you some about the GTC GPU Technology Conference highlights. So every year we have what we call GTC. I think this was the 8th one. It is really our developer conference, but as we've moved into the artificial intelligence and the machine learning era, we've begun to see much more demand across the industry. So it is also a bit of an industry customer event, in addition to being very highly technical and having lots of materials and resources for developers. So typically it's held in March or April. This year, for a variety of reasons, we moved it into May. But next year will be March 26th and 29th. But I also want to bring to your attention, we've started regionalizing this conference, and so there will be a GPU Technology Conference in Washington, D.C., November 1st and 2nd. So we'd certainly like to encourage you to consider attending that later in the year. So let's sort of dive in from the highlights of GTC. This is essentially a kind of a snapshot, a mini presentation of what Jensen was talking about in his keynote. Let's look at life after Moore's Law. We've got basically 40 years of microprocessor trending data here on the screen. And as you can see, single-threaded performance has started to tail off basically in the midst of between 2010 and 2020. But with the number of transistors shown on the slope, GPUs themselves are continuing to bring much better performance over time. So I'll bring to your attention the end of the road for general purpose processors. That's a quote from John Hennessy at Stanford University. So what we're seeing now is the rise of GPU computing. To the left is sort of the way we, in a very simple way, look at the stack with CUDA and the GPU architecture at the bottom, working up through systems and algorithms into applications. And again, the trend of single-threaded performance tailing off, really gaining about 1.1x year over year now. But GPU computing is sort of picking up where that leaves off. And we're growing on average about 1.5 times per year. And that trend continues to increase in terms of performance over time. So we're entering what we call the era of machine learning. There are 2 books that I'd like to encourage you, if you haven't seen them or haven't read them. The Master Algorithm by Pedro Domingos and A Quest for Intelligence by Fei-Fei Li. These are 2 well-known, respected AI researchers. Both of them give a very insightful view of sort of the beginnings of where machine learning has started and as well as where it's going over time. So there's another book that's on here that we don't have a snapshot of. That's by Yoshua Bengio and a couple of other authors, which is, to me, sort of the Bible or the handbook of machine learning. It's just called, Deep Learning? And I can get a snapshot of that for you. So NVIDIA historically has been known as a graphics company, but the architectures that we've brought to market actually have turned out to be optimal for doing lots and lots of parallel computation. And that very much is the workload of artificial intelligence. In many ways, if you boil it down, it really comes down to a 4x4 matrix multiply in many cases. So the architectures that we previously had brought to market for graphics have been very, very well suited for artificial intelligence. And so these are some of the, from left to right, the sort of areas that we've been working in. Machine learning frameworks and in GPU systems, as well as the GPU as a service, if you think of it that way. And then along here are some areas that we've been developing. We have NVIDIA AI Research Labs, providing internet services, also delving into healthcare, and reaching these technologies across our research. We have an inception program for startups, and then also into the enterprise, and then moving across into our SDK, into the automotive markets, and enabling robots as well as other technologies. At the start of the keynote, it's always good to have a very powerful demo, so we announced Project Holodeck. This was actually an interactive demo that was done with the CEO of Koenigsegg, which is an automotive, very high-end automotive design company. And we were bringing photorealistic models and interactive actual physics of the car itself in a collaborative environment. And this was done on stage live, as well as with the collaborators that were in Europe at the time. So Project Holodeck, more details of that will be coming out, but think of it as essentially what we can implement today in terms of the Star Trek holodeck, if you're familiar with that from the Star Trek Next Generation series. We've also been applying deep learning to ray tracing, making the algorithms essentially assess the quality, the visual quality of the image, and improve it over time using machine learning algorithms, and improving the actual quality. So that looks to be a photograph, but that's actually a ray traced rendering that's using deep learning to improve interactively the quality of the graphics over time. So one of the things that we're seeing is that model complexity, and when we refer to model, we mean the actual artificial intelligence model. The complexity is exploding over time. When Microsoft released ResNet, which is sort of the breakthrough in terms of accuracy and recognition, it took about 7 exaflops and 60 million parameters to train that model. More recently, Baidu, with their deep speech engine, got to 20 exaflops and 300 million parameters to train that model. And we're looking at Google's NMT in 2017 requiring over 100 exaflops and over 8.7 billion parameters. So we need to develop architectures that can handle this level of complexity. And as AI continues to evolve, this number of parameters and this amount of computing will continue to grow. So to address these challenges, we announced at GTC the Tesla V100. V is for Volta, and it is the densest circuit ever produced by humankind as far as we know. Those are some of the key details about it, but over 5,000 CUDA cores now. These are parallel execution floating point engines, and capable of up to 7.5 double precision floating point teraflops. So as we go into the machine learning space, machine learning doesn't really require as much in terms of double precision. They tend to use single precision. So in fact, you're looking at 15 teraflops of single precision, and then you can even go further down to 30 FP16 teraflops. And then we've also brought out a new feature in this chip that we call the Tensor Core, and we're able to do 120 teraflops of Tensor Core floating point math. They have 16 gig of memory on the card. Actually, I have an earlier generation of the This is the module before Volta. This is a Pascal module, but it uses very much the same design. You can pass it around. It can't do any harm to it. But we're using what we call high bandwidth memory. It is directly connected to the GPU and provides up to 900 gigabytes per second between the GPU. And we are now able, with NVLink and NVLink 2, to connect multiple GPUs together. So we brought out a new feature. This is new in Volta. It's not in Pascal. It's called the Tensor Core. Brad will be talking a little bit more in detail about the intrinsics of that. As you can see, Pascal on the left, and then the Volta Tensor Core. What we're actually able to do is increase throughput overall by 12x, being able to do a 4x4 matrix multiply and an add essentially in a single instruction cycle. So the idea is, lots and lots of these calculations need to be done both for the model training and for model inferencing, and this will provide the kind of performance that we saw those algorithms requiring on the previous slide. So if we compare this to Pascal, we've got 1.5 times the general purpose floating point operations for high performance computing. So all the traditional high performance computing workloads that we've seen in the past will get automatically accelerated, no need to change code. And in order to adopt these features, those codes will run unchanged. And then, as I mentioned, 12 times the tensor flops versus what you could do equivalently on the Pascal. And that's for model training, and then 6 times the tensor flop throughput for the inferencing workload. So that's a little bit about the hardware, but the hardware isn't terribly useful without some software on top of it. And in the machine learning world, we talk about frameworks. We talk about software stacks that have APIs and functions that perform an awful lot of, or all of, for the most part, the transformations that need to happen to the data, both on the model training as well as on the inferencing side. So we've taken the Caffe framework, as well as Microsoft's Cognitive Toolkit and MXNet, which is sort of a more modern machine learning framework. And we've provided acceleration in our CUDA and cuDNN libraries for this. And we've got some comparisons in terms of how the impact of the greater performance reduces the amount of time it takes to train a given model. So with our K80s, which are in many cases still a contemporary GPU in a number of research labs and companies around the world, it would take up to 30 hours to train the ResNet model. In Volta time frame, we're able to do it literally in less than about 8 hours, which is pretty significant. We're getting to be able to train ResNet in less than 8 hours. We also, using the Nickel collectives, which is a library for doing multi-GPU scaling, we were able to do the ResNet 50 with 64 V100s literally in about less than an hour, just about that time frame, which if you're familiar with the amount of time and complexity that it takes to do ResNet, and understandably you may not be yet, that's a pretty significant statistic. And then MXNet and the LSTM training were able to do significantly better performance and throughput on the Volta 100. Oh, I want to go back. So what we've done is taken the DGX, taken the Volta and the Pascal GPUs and put these into a what we call an AI supercomputer, and we call that the DGX-1. We've had that out for about a year and a half now with the Pascal. It had 8 Pascal GPUs in it, and we've actually announced in our bringing to market the Volta version of that. We expect to see those in the September-October timeframe. But this allows us to go from 8 days on a Titan X to train ResNet to 8 hours. And if you take the computational capability that's in those GPUs, it represents the equivalent of 400 servers in a traditional x86 server environment. So this is just a breakout of the actual layout of the system. And we've got 8 Volta GPUs arranged on a daughter card, and that is then married with a traditional x86 dual Broadwell server. We also announced the DGX Station. This is kind of a personal DGX. It's got 4 Tesla V100s, each with 16 gigabytes. Can be capable of nearly 500 tensor teraflops, 480 tensor teraflops. And those V100s are fully connected via NVLink. It's actually water-cooled and consumes about 1,500 watts. But it's a pretty beefy workstation to consider developing on. And that will be available in the September-October timeframe as well. Another architecture that we've actually brought to market is for cloud service providers. The Baidus, the Facebooks, the Googles of the world, Amazons, they actually have decided that they consume so many servers and so much resources that they're in a position to actually dictate to system vendors what the architecture should look like. Instead of them just buying what's available from the vendors, they're actually dictating the terms and conditions of what they want to bring into their data centers. So the HGX is a reference architecture that was co-developed with multiple players in the industry, H standing for hyperscaler. And so over time, you'll begin to hear about these making their way into data centers. It's not a traditional commercially available off-the-shelf product, but it's an example of where we can take these architectures and make them available in the industry. So probably, I would say mid-2018, you'll see Google and Amazon and Baidu and so forth and Facebook beginning to deploy these. And we support deep learning operations, deep learning software, as well as our grid remote software capability on this system. We've also taken a lot of the software experience and knowledge that we have and put this into what we call Tensor RT, or real-time inferencing library. So think of it as a compiler for deep learning inferencing. How many people here would say already pretty familiar with machine learning and deep learning? Okay, good. So just stepping back a bit, I know I've been throwing a lot of terms around, but there's 2 key parts of machine learning workloads. One is the notion of training a model, actually showing it examples of data, building up a generalized understanding of what the data is. And then the other part of that is what we call inferencing, which means actually using that model to identify or look for patterns, look for things that we're trying to determine. So Tensor RT is meant to accelerate the actual inferencing side of the workload. We have in the Pascal family, we actually have a GPU that I haven't talked about here. It's available today. It's called the P40. We also have its little brother called the P4, which is the P40 basically slimmed down into 1/3. And before the HGX, that was how the cloud service providers were building out architectures for doing large-scale inferencing. They would buy literally thousands of the P4 cards and deploy those at scale. And so the Tensor RT framework is meant to accelerate and make use of that hardware. So we support graph optimizations. We have GPU-specific optimizations. And Tensor RT can import models that have already been trained previously in both Caffe and TensorFlow, and then begin to run inferencing across that optimized infrastructure. So example here on the right is increasing throughput over time and reducing latency using the ResNet 50 model. And we're able to take that from a Broadwell platform without any GPU acceleration, 20 milliseconds, down to less than 10 milliseconds. And with a Volta 100, with the V100, we're taking that down to 7 milliseconds. So I mentioned previously the HGX. The point of this is really to, if you're imagining a Facebook or a Google trying to recognize cats or recognize dogs across a huge swath of data, this is the kind of scale that they want to be able to build out at. So roughly, you've got 300,000 inferences per second required in the data center, and those are sort of the statistics that we're shooting for and able to deliver. So we have our deep learning software stack, starting from at the very bottom, the system, adding in the GPU, the operating system, and the CUDA drivers. This is a very high-level depiction of many of the pieces and parts that we're going to be working with over today and tomorrow. We've also moved into what we call the NVIDIA GPU Cloud. Our DGX systems, in addition to just getting hardware, we also provide a software and support contract that comes with it. And what the advantage of that is, when you're trying to actually do model training or inferencing, what you don't want to be doing is running around downloading all of the latest frameworks, finding all of the drivers, doing the compiling, tuning them, and integrating them. All this work is already done for you. So we have a portal that DGX1 and DGX Station customers can actually go and access online, and they have direct access to all of the optimized frameworks that we support. And it's essentially an online registry of containers. I should step back. So the way that we're delivering the frameworks is using what we call NVIDIA Docker containers. It's an abstraction for being able to take a huge stack of software and spin it up essentially as a virtual machine with very low overhead. So that's sort of the basic construct that we're working with in terms of how to distribute the software in that environment. And we will enable customers to be able to access this. You can also have your own private cloud and access the contents of the registry and be able to build your own networks. And we also will provide this for cloud service providers who want to be able to take advantage of this at scale as well. We're entering into the beta phase now, but one of the nice things about GPU Cloud and that we're providing is we also provide beta access to new frameworks and new drivers as they come online. So just some sort of statistical graphs about what's happened in GPU computing from, let's say, back in 2013 with the K20 and the K40 series. These are typical, what we call molecular modeling workloads using Amber. And using the P100, we're actually able to get significantly greater amounts of computation done in essentially the same time. In molecular modeling, the figure of merit, or the metric that is measured, is the number of nanoseconds that can be simulated in a given day. And so we're massively increasing that with the P100 GPU. And then on the model training side, the GoogleNet performance, we're able to significantly increase the performance of that workload over time using the DGX Volta system. And those were measured in our labs just in the last few months. Another area that NVIDIA is moving into very aggressively is autonomous vehicles, autonomous cars. We have 5 basic brands, if you will. NVIDIA may be, in some people's eyes, sort of a big green box, and you've just known us for GPU computing. But in fact, from our days of starting as a graphics systems provider, we've iterated on the GeForce line, and then that turned into Quadro for professional visualization. And then we brought out Tesla for doing high-performance computing. And then we also have our remote graphics capability, which we call NVIDIA Grid. And then at the end of that list is Tegra, which is the embedded version of a GPU, which is optimized for a low-power, ruggedized environment. And so we've taken the Tegra chips and integrated these into what we call a Drive PX package, which is aimed at automotive and embedded applications for being able to do self-driving vehicles. We announced the Drive PX Javier. This is actually based on dual ARM processors. So we've integrated a GPU with an ARM processor and provide that as an integrated package. And these will get us up to level 4 and level 5 autonomous vehicles. And this is just kind of a snapshot of the sort of workload that's involved in trying to teach a car or enable a car to drive itself. It's got to be able to figure out where it is. It needs to be able to sort out path planning, the ability to actually perceive its environment around it. So cars today will, autonomous cars, the prototype cars, will have up to 12 camera inputs Those are HD camera inputs that all have to go and actually be sorted in real time. And this is integrated with computer vision libraries, and then the CUDA acceleration that comes with that, and the operating system that essentially provides all those services in a full integrated package. In addition to autonomous vehicles, we're also moving into the robotics area. And this is sort of the life cycle of a robot, the notion of being able to see, hear, and touch, as well as learn, formulate a plan, and then take action and continue to evolve that cycle. This is actually an example of a robot using GPUs to, actually, let me go back up, play hockey in this case. It's actually looking at the floor. It recognizes that there's a puck. It has a hockey stick in its hand, and its goal is to put that puck in the goal. And over time, it evolves its capability to recognize where it is, the goal, formulating the plan to actually put the puck in the net. And I thought this would play, but I don't think I have the video loaded for that. So in order to bring all this into reality, we created a robot simulator. Rather than going through the expense and potentially the risk of either damaging the robot or the human near the robot, we've actually built a simulator that takes all of that software stack and then actually allows you to, in the simulator, determine what the outcomes would be based on the algorithms that you've developed and put into the robot. So it's a combination of the definition file. There's actually a file format that defines what a robot is, including its model, including all of its appendages and arms and degrees of freedom. And then we've integrated that with the OpenAI Gym, which is a set of software for being able to express machine learning algorithms for a variety of tasks. And then the robot simulator works on the NVIDIA GPU along with a computer and a virtual Jetson module. So through this process, you're able to iterate through this loop and continue to refine and evolve what that robot's, if you will, what its master plan will be. So this is kind of a snapshot of the ecosystem that serves this AI revolution in the robotics and autonomous vehicle space. The V100, the Tensor Core operations, and then short list, if you will, of providers and industry adoptees of this technology, taking advantage of the NVIDIA GPU Cloud, as well as the DGX1 and DGX Station. And then Isaac is the name of the robotics simulator. So that, in a nutshell, was GTC. And I invite you to, if any of that either confused you or piqued your interest, all of those sessions are recorded as video, and they're available on the website now. Jensen's keynote runs at about an hour and a half, so that might be a bit long for you to want to sit through, but it does provide a lot more drill-down detail on some of what we covered there. So any questions, thoughts, contributions? No. Well, I'd like to turn it over to Brad Palmer. He's going to take us into the next level of detail. So with that, thanks very much. That's my power, so I'll take the power. Yeah, you.
Good morning, everyone. I got one. Okay. So I'm gonna start today talking about just GPU acceleration in general. So it's not tomorrow is our big AI day. We're going to be doing the deep learning workshops, and that's part of the whole GPU acceleration universe, if you will. But I'm going to kind of take it down another level and talk about the kind of the fundamentals of acceleration for GPUs. So thinking about high-performance computing in general, right? We've got a number of challenges, right? There are challenging algorithms and simulators and so forth, and they're very difficult to. It's very challenging for a single CPU system to do it and to run it. And so over time, we've been making CPUs faster, but the problem is that's peaking out. So we've moved on to parallelizing code and adding CPUs and CPU cores, but still building one giant system with a lot of CPUs is also very challenging and expensive. So we've been implementing distributed computing. So now we have computing clusters. So they've got multiple processors, multiple cores, multiple nodes. But then if you try to extend that, building a giant cluster is very, very expensive. And it's also very resource, it's a resource hog in terms of power and cooling. And so this is where hardware acceleration can really make a difference. You can have denser systems with much more power concentrated in each one. And another thing that's fundamental here to consider is CPUs really, from the start, have been designed to hide latency. So all the tricks that are done in the CPU architecture are there to give you that faster response, to make it more of an interactive experience using that CPU. GPUs, on the other hand, are really all about throughput. So you've got this trade-off. It's a fundamental trade-off between latency and throughput. And really, it's the marriage of the CPU and the GPU together that gives you that powerful computing platform. So I know Barton threw this up here already. We talk about Moore's Law. We've probably all heard Moore's Law, and also sort of a corollary from an Intel executive, David House. So Moore's Law roughly says that microprocessors, the transistors density is going to double every 2 years. But what the Intel exec sort of refashioned that, and that's what we sort of generally think of Moore's Law, is that every 18 months we're going to double chip performance, just raw performance. But the challenge here is that, I mean, clearly from this blue line, that isn't happening with single-threaded performance, and part of that has to do with power and power density. And there's a term called Dennard Scaling, which was postulated that roughly as transistors get smaller, as you increase the density, the power density will stay constant. So you're fitting more transistors into the same amount of space, but your power density is not changing, and that's actually broken down in the last 10 years. And because we've reached the level of density where it's generating a lot of heat. Its current leakage is causing a lot of heat to be produced, and that's just making it impractical to run these transistors at higher and higher clock speeds. And so for CPUs, we've been building them out into multiple cores. We haven't been making them necessarily a lot faster in terms of scaling up. We've been scaling them into multiple cores. And so that's where that trend is going. But as Barton pointed out, with GPUs, because they're designed for throughput, we don't have those same kind of limitations at this point. And so we've been able to continue to increase density and performance at roughly 1.5 times a year. And it looks like that's going to continue. So if we're looking to accelerate computing, really this is one of the key areas we want to look at is not wholly relying on the CPU, but look for ways to offload some of that to an accelerating technology. And this is bared out really when you look at the top 500 list of supercomputers. Right up there, number 3 and 4 on the list, they're achieving those high levels of performance with acceleration from GPUs. So the supercomputing community definitely sees the value in acceleration. And in fact, those the bottom two there, the Facebook and our own Saturn V systems, those are made with the DGX systems that Barton referred to, and they're really like deep learning supercomputers. And they're extremely dense, extremely high performance, and they're not really necessarily used for those same high performance workloads. They're being used for deep learning, but if you run LinPack on them, they hit the top 500 list. So this is sort of the the trend in high performance computing really is shifting a lot towards the use of GPUs. And you can't talk about HPC without talking about Exascale, because we're and it's sort of like a goal, it's a benchmark, it's a watermark that we're trying to achieve, and that is creating computing systems that have 1,000 times the performance that they had in 2008. Huge, huge ambitious goal, but there's a lot of motivation behind it because of what we're capable of doing when we have greater computing power. The kinds of things that we're not doing now, the things that we don't do because we just don't, we can think of them, but we don't have the resources, the computing resources to do them. And this, as we move to Exascale, we're going to be able to do more of those things. It's going to, make a huge impact. And towards that end, Oak Ridge National Lab is going to be getting a new supercomputer called Summit, and it's going to be put in place later this year and be up and running next year. And I don't have the exact numbers on the performance yet. They're still they're still in flux, but it's replacing the Titan computer, which if you recall, was on that list at number 4, I think. And this is, you can see the scale at which this is increasing performance, and it's implemented using IBM Power 9 systems and our Volta GPUs. And what's interesting here is, you look at the number of compute nodes, 18,000 for Titan. Here we're down at 3,400, but the performance difference is enormous. So this is the density and concentrating this computing power, and it's really because there are these GPUs and the high-speed interconnect between the GPUs that gets us to that kind of performance level.
And that actually was something I didn't mention in the overview also support the power CPU architecture. So that actually was brought into being as part of the partnership with IBM to win these two supercomputing systems. So we may have traditionally thought of NVIDIA in that x86 server or x86 workstation scenario, but we also are integrated with and work with the IBM power or open power architecture.
Right.
And in fact, there's some advantages to the way that hardware has been implemented versus x86 that provide this kind of throughput over and above an x86.
Which I will be talking about.
Very good. I don't steal your.
So let's take a step back and I just want to talk about how do GPUs accelerate? How does it really work? Well, there's a lot of with code. There's generally the system is spending most of its time on a very small set of routines, often very repetitive parallel routines. That's the part that we accelerate with GPUs. So the sequential CPU code, sequential code, runs great on the CPU. That's not the part that we want to accelerate on GPUs. We want to take those highly parallel routines and put them on a piece of hardware that's designed to just do that really well, which is the GPU. And that's where you can get these tremendous speed ups, is going in and looking at that code and finding those places and speeding that up. And when Matt is here this afternoon, he'll show how to use OpenACC to do that with code. And I'm going to talk a little bit about OpenACC as well. But that's part of the analysis of the code, is to go and find those places where you can accelerate. So a little bit of history. I know Barton referred to this. NVIDIA got started making graphics chips back in 1999, I think it was, consolidating all those functions into a single chip. But it was really 2006, 2007 when we kind of opened up the interface to programming, to actually taking general purpose workloads and putting them on the GPU instead of just being graphics specific. And that's what we call CUDA, which the original name for it was the CUDA Unified Device Architecture. And Compute Unified. Did I not say that? And so this is just a history of kind of the progression of where things went after we opened that up, and you can see Oak Ridge, the Oak Ridge Titan system there, and then really most recently it's been huge strides in the deep learning space. So what is CUDA? CUDA is really it's a platform, an API. There are a lot of components to it. We just throw out CUDA, but it's really an environment for programming GPUs. And as I said, it's the Compute Unified Device Architecture. It's compatible from the beginning. It was designed to work across the product line and to be compatible from generation to generation. And I think this is key to from an engineering perspective. This was just a really great design decision, because there is just one CUDA. I mean, there's just one interface, and every successive generation, additional features are added, and they can take advantage of the new architectures. But the existing interfaces continue to work, and they'll work on across the product line, from desktop systems and mobile systems and high performance data center systems. And that's the way it was designed, and that creates this great amount of flexibility. So if you've got an NVIDIA GPU in your laptop, you can use that. You can use that to run CUDA. You can run CUDA acceleration on that. So, all the way up to the data center. So as Barton pointed out, it's an ecosystem that supports Power, ARM, and x86 currently. It's designed to be compatible across different architectures. And I'm going to dive more into some of these other elements. And as I said, CUDA works across the whole product family, and there are, the consumer cards, the GeForce cards, and they're using, all of these are using the Pascal architecture, our current architecture, but Volta is coming soon. And we have professional graphics, we have systems for hyperscale and for specializing in different aspects of deep learning. The P40, for instance, is really very well suited to doing inference at scale, and whereas the P100 is really a great general purpose GPU and is targeted right at training for deep learning. So, what it comes down to is there are essentially 4 ways you can accelerate workloads with GPUs. And I'm going to talk a little bit about each of these. But if you've got, you have a task and you're looking for ways to accelerate, for it to run faster, there are some guides here about how you can go about doing that. So the first is going to be applications. There are many accelerated GPU accelerated applications. So, yeah, and you may already be using one of those scientific apps or other applications, both from third party, from ISVs, from software vendors, or from open source community. And I mean, let's face it, using an application is a lot easier than writing code from scratch. And there are GPU accelerated versions of them out there. And there are also, as I said, there are things that you just simply are not practical to do on a CPU. They just take too long. Simulations that might run for weeks or months on a CPU-only environment. It's not practical for you to do that. You're not gonna meet your deadlines. You're not gonna gain any insight. By the time it's actually finished, you'll have moved on to some other idea. So you need to have that. You need to have that feedback from the work you're doing, and so things that maybe wouldn't have gotten done in a CPU-only environment are possible with accelerated applications like this. So this is kind of a dated survey from Intersect 360, but essentially, what they found is 9 of the top 10 applications, scientific applications, did have acceleration, did have GPU acceleration. And over here on the right are the top 25 applications in the survey, and this is a little dated, as I said, because Gaussian now has been accelerated. And games is being worked on. But another thing to point out here is some popular functions accelerated. So it's not always an all or nothing thing, right? A lot of these big codes have all these different sections to them that have specific areas of computation that you want to do, and you may not be using them all. You may be using just part of it, and so these get accelerated over time. It's not always just not accelerated or accelerated. So, for instance, there are some weather codes like WRF. And WRF is a huge code base, and it's written for, and it's, different modules of that are systematically being accelerated, and NVIDIA is working a lot to help make that happen. But it's a huge undertaking, and yet for every release, it's faster. It's faster when you're using GPUs because each of these sections is getting accelerated. So the point is that it's not, it can be an incremental process, and so keep an eye out on applications to see how they're progressing in their acceleration. Now, at NVIDIA, on our website, which I listed the URL here, we publish a catalog of accelerated applications. There are over 400 in 11 different categories. I'm going to show some examples in a couple of areas here. But you can see, all these areas, and so it might be that you're already using one of these apps, or it's a good, it's a good fit for the work you're doing. And so I encourage you to take a look at this and see if you've got any applications in there that you're already using. Here's some quantum chemistry apps that have been accelerated. And we've got Gaussian up there now. So any of you familiar with these? See on that list, we've also have molecular dynamics applications, just as another example of a category. All these have been accelerated to run on GPUs as well. Any questions about applications and acceleration of applications?
Yeah, you've all been very quiet and very fine so far. There's got to be questions of some kind so far.
All right, I'll get something. I'll generate some questions with the next one, I think. Libraries. Okay, so-called drop-in acceleration. Well, I mean, if you've got existing code that you wrote or that you're using or that was handed to you, or that you're collaborating on, chances are you're using, you're using some libraries out there, right? And chances are good that there is a GPU accelerated version of that library, or something that's doing a similar function that you could drop into those places where it's spending the most time. It's doing these parallel tasks on the CPU, and you can. If you can find these libraries and drop them in, that's a pretty straightforward way of accelerating that application. So here's just a small sample of all the libraries that are out there, and at the bottom here is there'll be the complete list. So this is on the NVIDIA developer site, and I encourage you to go to developer.nvidia.com. They just want you to register with your email, and there's just a wealth of information there about GPU accelerations. There are really interesting blog posts about how GPUs are being utilized in various endeavors, and it's also a way to access libraries and a whole bunch of other information, compatible applications and middleware. It's a great resource. But let's see. So we're going to talk more about the deep neural network library tomorrow. But let's see, for instance, we've got the NVBio. It's a C++ framework for sequence analysis. That's an accelerated library. GPP is for GIS systems, and I mean you can see all the variety of areas where there are accelerated libraries. Let's see. I'm gonna click through this. As I think Barton was mentioning, for deep learning, there are those who write low-level code for deep learning. I mean they're right down there at the base level. But generally, people are using frameworks because it just the whole workflow for developing models and training them and doing inference is greatly streamlined by using one of the frameworks, or maybe even multiple frameworks, because they all have their idiosyncrasies, their advantages. all of the major frameworks and some of the not so major frameworks have been accelerated to utilize GPUs. So what that, and it's more than just that they've been accelerated. NVIDIA, we aggressively work at accelerating them. So we have a team of engineers, and that's what they do, is they work with all the open source teams, and they're integrating our libraries and working on accelerating specific functions in all of these frameworks. And they're putting that code back into the main code branch. So, this is part of how we're involved and how we're doing this. And we're promoting the use of GPUs, but we're really putting out a lot of the all this work we're putting it back into the community to accelerate these frameworks. And the same is true for the scientific libraries as well, where we're putting in the acceleration. Talk a little bit about the deep learning ecosystem here, and like I was saying, the frameworks kind of sit at this level in the middle here. We have our own deep learning. We call it an SDK. It's a collection of tools and libraries, and most notably is the CUDA, which I'll talk more about in a second here. We also have the DeepStream SDK, which is for working with video. The basic linear algebra library is part of CUDA, but it's fundamental to deep learning. Sparse matrix library for matrix operations, sparse matrix operations, and then NCCL for essentially inter GPU communication. So when you scale beyond a single GPU, then your model is going to require some communication between the code running on separate GPUs. And we developed this library and also some technology to speed up that communication. So let's talk about CUDA. It's our accelerated library for deep learning. So it has things like forward and backward convolution routines. It has a lot of kind of the fundamental algorithms that you'd be building into these frameworks. You can call them directly, but generally these are being built into these frameworks. And so I just wanted to touch on CUDA, and we'll talk a little bit more about that tomorrow. Next is OpenACC. Now, Matt's going to be here this afternoon. You're going to get to. He's going to be remotely here. Right. He'll be virtually here this afternoon, and he's going to do more of a deep dive into OpenACC. But OpenACC is really pretty awesome because it's directive based. So it's really great for taking existing code and accelerating it for GPUs, or also for multiple cores or multiple. It's really compatible with OpenMP and MPI as well. So you're able to use directives in the code, and then you can build it for CPUs, you can build it for GPUs, you have that flexibility. And it's very, very popular with big, monstrous existing code base, like, for instance, the computational chemistry Gaussian. Gaussian was the monster code base, and it means you're not disrupting the existing code. You're just putting in these hints for the compiler. So it's, let's see. So we have, I think I'll let Matt talk about this more. I think I'll just show you some examples here of codes that have been accelerated using OpenACC. And this is kind of interesting because they talk, there are some stats here on how they, how the performance increase they got, but also the amount of time it took. Like for instance, in this app, they got a 12x speed up for a week's worth of work, which is pretty phenomenal. This maybe would be a little more realistic here. Maybe spend 4 weeks putting in the OpenACC directives and really digging down into analyzing the code, running the profiler, looking at the code and finding ways to squeeze out more acceleration. But this gives you an idea of how that it can pay off pretty quickly to be adding this, and it's incremental as well. So you can, you've got a routine that's just the biggest hog in the program. Just accelerate that. You don't have to deal with the rest of it. It doesn't. You can get that positive result right away, and it's just a directive. So if it doesn't work, it doesn't hurt anything. It's just a compiler flag. So to use OpenACC, you need to use the PGI compilers. And if you didn't know about PGI or were familiar with it in the past, there's a community version of it now, and I know Matt's going to talk about this too. But this is open and available for everyone, and it's all the features, right? It's not some dumbed down light version that's free. This is everything. The only thing that you don't get when you use the community version is you don't get updates as often, and you don't get support. You have to do community support, but it's and it says license annual. It's just you need to renew. You need to just say, yeah, I'm still using it.
You need to renew and you need to install the right version. So we want to
right.
keep people moving in absolutely.
Good point. Yeah.
But until we did that, there really wasn't a way to practically get access to those compilers, and they really unlock all the performance and all the feature sets. So it's a significant decision that was made. Is literally to put the entire compiler set documentation, the whole ball of wax is out there for no cost.
So just a little illustration of how directives work, what they look like. Just picking out a section of code and accelerating it. This is as easy as it gets, and then there are additional layers on top of that, so you can get greater efficiency and greater acceleration. But at the simplest level, that's it. That has been accelerated for GPUs with a compile. It's done. So that's OpenACC. Now, the fourth way really is the most flexible, but it's also the most work, and that is to really write the code specifically to run on to be accelerated on GPUs, to run on GPUs. And that's using CUDA libraries, but it's also using additional things in the API that lets you go down to that level. So this just illustrates kind of a very simple example of accelerating a SAXPY routine here, and I'll talk about this more in the next section. But essentially, you've got a specifier at the top here. You've got some built-in parameters that are filled in for you. You just need to include them in your code, and then you have a way to invoke the kernel, as we call it, which is the section of code that's going to run on the GPU. We call them kernels. So more on that later. So what's in the CUDA toolkit? When you download CUDA, what do you get? Well, it's got a lot of libraries that come with it. Sparse and direct solvers. It's got Graph Analytics is a new library that we're continuing to add to. There's a fast Fourier transform, basic linear algebra. Also, you get compilers, a profiler, debugger, memory analyzer, and there's tons of documentation and code examples. So that's kind of what the whole thing you get with the CUDA toolkit. And so you're and this is, the overall development environment includes PGI. So for Fortran, you're going to be using the PGI compiler. There's also a C++ compiler with PGI, but there's the NVCC comes with the CUDA toolkit. So yeah, there's a variety of profilers, debuggers, memory checkers, as I said. So let's see. I have some examples here, which are kind of interesting in terms of where GPUs are being utilized to accelerate code. And there's some big projects. I think the Large Hadron Collider, that's a pretty big project, and the kind of data that's being collected, it's massive. And so GPUs are being utilized to accelerate that processing. It's just a massive amount of data that's being collected. For NOAA is using GPUs on their supercomputers for modeling the atmosphere, and they're able to. And I think this really what they're able to do is get a higher level of detail, a model that's much more specific and higher resolution than they were able to do before when it wasn't accelerated. And this is really the promise of being able to move to exascale, is the example of the kinds of things that can be done. Here's an example for HIV. I'm going to move through these as well. So I want to point out, as I had said, there are a lot of resources available on the developer site, and there are also, this is kind of hard to read, but there's also training available. So online, there's just a lot of resources for learning more about accelerating applications, and there are also teaching kits. So we produce teaching kits for kind of like getting started for college level classes in GPU computing, and also deep learning and embedded processing with GPUs. So we can get more information on that if you like. We're going to be using tomorrow QuickLab to do some of the Deep Learning Institute. We're going to do 3 of those labs tomorrow. But there are also labs for OpenACC, for CUDA, and they are either free or inexpensive at NVIDIAQuickLab.com. So that's another resource, and you can look at the catalog and see what's available. So those are kind of nice ways to kind of come up to speed quickly on these topics. So let's see, how are we doing? Pretty close. So we talked about the 4 ways to accelerate workloads with GPUs, and I guess that was what I had for that section.